on Bayesian classifiers, and I had hoped to do like a walkthrough with Python. I got about 2/3 of the way there, so the Python code isn't finished. So I'll go through the slides, and then if we still have time, we can kind of go over the code I've written and maybe even finish it here, if you guys want to do like a pure programming. But we'll just run through, and then we'll see how far we get. A lot of where I was learning about Bayesian classifiers and using Python for it was this book called Thinking Bayes, and it's an excellent resource. It's free online. There's a GitHub repository where you can download all of the code that he goes over in the book. Very slow, detailed examples, and there's enough statistics that you do get a good understanding, and you understand the mechanics of it underneath. But then it's straight into real world examples where you can apply it. I thought it was probably the best resource I've ever come across on learning classifiers for using Python. He's written a lot of the classes and stuff too. The way that he writes his code is not necessarily the way I would do it, so I kind of rewrote some of the stuff. For someone who's coming in as a complete beginner, there is examples that they can kind of pull from. So I put that up there. So a brief history of Bayes' theorem. How many people are familiar with Bayes' theorem? I see a lot of statisticians in the room. I should probably tread very, very softly now, seeing all the hands go up. But the Bayes' theorem is an equation that's credited to Thomas Bayes. It was a statistician and mathematician. And the concept of Bayes' theorem was allowing you to update your belief based on new information. That's kind of the fundamental concept of it. It's often put against what's called frequentist statistics, where it's looking at how over time frequently something occurs and coming up with a probability based on that. So say, if I observed 100 flights, I looked at a data set and I observed 100 flights, and 30 of those flights ended in plane crashes, I could say, okay, well, the probability of plane crashes is about 30%. Bayes comes at it differently and says, I haven't observed any plane crashes. And I have no idea what's going to happen next. And so you form a hypothesis and you say, well, what do I believe is likely to occur? And then as I collect data, meaning every flight that I go on, every flight I observe, I can update my belief about whether or not the plane ride is going to end in a crash. So for Bayes' theorem, it's broken into 4 parts, where you have the prior, which is your hypothesis, saying what do I believe will happen regardless of any data, or what are the outcomes that I'm looking for. You have the likelihood, which is the probability of the data given the hypothesis. So if you're looking at the plane crash example, the data would be flights that ended or that crashed due to a malfunction or something like that, and then you'd say, well, my hypothesis is there's a 50% chance that the plane will crash, and then the data says that there's an engine malfunction, and you're able to compute the probability of the data based on that. The normalizing constant is an interesting one, and it's actually, I'll talk about it, but it's not necessary for if you're using classifiers in Bayes. But for the theorem, it's what's the probability of the data under any hypothesis. And then the posterior is what's the probability, that's what we're computing. What's the probability of the hypothesis given the data that we've observed. So the prior is what do you believe about a situation? And in the book, he kind of goes through some examples of you can have a hypothesis that is well informed by a bunch of research, or you can have a hypothesis that is wide open to interpretation as possible. And the two approaches are, do I want to start with something that is as general and informed by the data that I'm going to be collecting, or do I want something that's backed up by research? A good example of this that he goes through in the book is a train problem, saying given that you see a train and it's labeled 60, can you estimate how many are in the company's overall? And one of the things that he he highlights in that for coming up with your hypothesis is, I could do research on, in my region, the size of what's the largest train manufacturer, what's the smallest, and that would be more of an informed, a well-informed prior, saying, can I look at the data that's available and come up with a hypothesis that's reasonable for the domain, versus can I just start with something that allows everything to be equally likely. Another example is if you're doing like a classification of male versus female, and it's a binary, so your hypothesis would be 50%. My hypothesis is 50% likely. Or you could do a study in the room and say I have this many men, I have this many women. My hypothesis is it's 60% leaning male, 40% female. And that's a way to start the problem from a different standpoint, and that does have an effect on the outcome. The likelihood is the probability of the data given the hypothesis, so how likely would it be to observe this data if my hypothesis is true? So saying that given the study that I've done on the room and male versus female, that with 60% male, then the observation that I see, or the data point is I observe a female, how likely is that? Or given two together, say male and female and age, if you come up with age ranges for male and female, and then you say, okay, given that it's a male, what's the likelihood that I would see this age range? And you come up with a probability for that. The normalizing constant is the probability of the data under any hypothesis, and oftentimes this is the hardest thing to compute because you have to think about just a wide open-ended question. What he talks about in the book, which I thought was really helpful, because I spent a lot of time struggling with this when I was building my first Bayes classifier, was are there things that we can do to simplify, and the thing that he brings out is choose a hypothesis that's mutually exclusive. So saying only one of the given options could be true at any given time. So it cannot be a male and a female. It's one or the other. And then come up with in your classifier a range of hypotheses that are collectively exhaustive. It has to be one of these things. So if it was a plane crash, the only two things we'd be considering was, did the flight end without a crash or did it end with a crash? And we're not classifying any other outcome. Those are the only two outcomes for the flight. Did it arrive or did it crash? If you do that, then you can use the law of total probability and say that your normalizing constant is just the addition of the data under each of the hypotheses. It's not needed in most classifiers because when you're looking at a classifier using Bayes' theorem, you compute the probability for each of your scenarios, and then you choose the maximum. So you just say, what's the maximum of all the different probabilities for each case of the hypothesis? So in male versus female, what's the probability that it's male? What's the probability that it's female? And then just choose the maximum value for that. At that point, the normalizing constant is going to be the same for each of those. So if you're not determined in like the relevance of, okay, is it how likely is it to be male versus how likely is it to be female, then you can just drop the normalizing constant. And that was something that it simplifies a lot of the problems when you're collecting it, because you can spend a lot less time in that area. Yeah, the same thing. So when you're classifying, you'll compute each hypothesis and choose the maximum likelihood there. Oops, this is the wrong presentation. So I wanted to work through an example. Unfortunately, I wasn't able to write all of the code for it, so we can go through that now. But the problem is, based on a quote, could I tell if you're a man or a woman? And the training data would be, we could pull a quote or find an area where we had it labeled already. The test data would then be submit a quote afterwards, or pull a quote from the internet that we already knew that was labeled. So I started to go through that. In doing a labeled text question, quotes was easy because I could very quickly find something. So what I did, I found, I can't move that, can I?
Can I ask you a question about that?
Yeah.
Concept in general.
Mm-hmm.
So is the notion that if you don't have that data, you can just assume a kind of a normal distribution, which will work against until you're able to assemble enough data
So
to come up with a probability?
yeah, so that's why it's a naive base. You kind of just assume there's a couple assumptions. One is that your features are going to be independent of each other, and that I'm pretty sure that's the underlying assumption for the naive part, that it is going to be a somewhat normal distribution. There's things you can do. One of the examples when I was building one was find ways to transform your data to a normal distribution. So I had a lot of data that was heavily skewed, and then I was able to do a log transform to get it close to that. One of the benefits is because you're basing it off like a probability distribution. And I'll talk about this real quick. I didn't get a chance to put some slides together on that. The benefit is it's very quick. It's easy to ingest new data very, very quickly in a base classifier, which is why they're used in like online machine learning systems, which are being trained on data that's coming in, because you can view data, get more data, recompute the distribution with just one look through on the data set. So like a good example of that was like word count. So if we're looking at documents and we have documents that we know and we want to continue to train the model as more information comes in, we just have to do word counts and do a distribution of the words based on this type of document, that type of document. We can continue to update the classifier with every new piece of observed data. So they work really well with like a data stream or something like that, or something that has a large amount of training data that you want to compute some things about it quickly. Does that kind of answer the question there?
Yeah.
This is
It's pretty hot. I mean, it's pretty far out that he thought of this. I mean, back.
Oh yeah. And there's so much more. There's so many more layers of complexity to base classifiers. You can get into classifiers that are more suited to certain types of distribution. So when you get into continuous variables, oftentimes it'll be a Gaussian naive-based classifier. I think there's some extent. I was reading a little bit about like Bernoulli-based classifiers, and so it's a concept that it applies to a lot of different scenarios, and it's very flexible. But then at that point, I mean, you can get layers and layers and layers deep into the statistics. But for like just a naive base, it's a simple way to get started on a classification problem, and it could even be a way to benchmark other classification techniques and say, if I set something up naive base very simple, can I get a sense of how accurate my things on top of that will be? Are there any questions about that? Are any questions in general? Okay. So I'll start to go through what I was trying to get at with the code, and we'll see if we can complete it with a little pair program. So what I had come up with, I was able to find a website that had just text that I could copy.
Oh. Can you make it larger?
You're trying to ask authorship?
Mm-hmm. So I was trying to see if I could find like a large corpus of text that would have been, this is examples of male writing, this is examples of female writing. I couldn't do that, and then Steve had the idea of just do Winston Churchill quotes versus Margaret Thatcher quotes. I was like, oh, that's a really good idea, because a quote, you have the author, you can generally tell if it's male or female. Then the problem was there's not a lot of Winston Churchill quotes out there that you can just pull down as a CSV.
Might also be a little idiosyncratic, right? I mean, not everybody like, oh, no, one doesn't like Winston.
Right. So that, that's another. So I was trying to think of something just kind of simple we could get off the ground. So I found a website that they had quotes by women and quotes by men, and it was something I could copy and paste in this kind of format. So the first thing I needed to do was do a little bit of data cleanup. For this, I'm not using anything out there already. There is stuff in scikit-learn for doing Bayes classifiers. There's a couple other libraries for Bayes. But with Bayesian classifiers, it's often so simple to implement. For at least starting, I think it's a good exercise to go through writing it yourself. And it's one of the machine learning techniques that it's simple enough that you can do pretty easily with just a basic understanding of either R or Python or whatever language you're writing in. When I was working with them, I downloaded the scikit-learn library. I started to play around with it. I think there was something in stats models as well. And I was spending more time trying to learn the API than I was actually working on the problem. So I was like, all right, well, I'm just going to write from scratch. And it turned out to be pretty simple. And that depends on the data. When you start mixing a lot of different data types, that's where you're probably going to want to tend toward using a package or something that's a little more complex, because it's going to have a lot of built-in stuff for you for making sure that you're computing things accurately. So what I started with was a simple script to clean the data and get it in a place that I could read it in.
I don't think your terminal's being shared. Oh. Just have to check the windows.
Edit.
Click on your name. Pop box. There you go. You can collapse this thing by hitting that box. Get it clear away.
I don't know if that's actually sharing. If I do multiple ones. There we go. So this is just a real simple, open a text file, remove the author by looking for the dash there, so delete those lines, and then there was a lot of spaces in new lines. So if the line length was equal to 1, skip that line as well, and then write it out to a file. So my end result ended up being and this is the men's file. So I basically have a big blob of text now. This one was simpler because I'm not looking to do a whole lot. There's not multiple documents. This is just a blob of text that I've labeled as I knew this was a male author. And then I did the same thing for the women's file. From there, there's a couple, I was reading on Stack Overflow what's some quick ways to kind of clean and normalize the text a little bit. So removing punctuation. There's a little function to just strip out commas, colons, all that other stuff. Convert the text to lowercase, and then a real simple regex command to split the text on a word. Regex can identify. Does that need to be, can I make that larger? The other thing, so now I open the clean file, which is just a blob of text. I do the two functions up there to tokenize, and then I get counts function, which just goes through and says for the words, count up the occurrences, and then make a dictionary of that. So then I have my dictionary for men and my dictionary for women. And this is what I was working on right before I had to come over here. How do I combine those into my vocabulary dictionary? So I have a master list of here's all the words that I've seen. So as I come into the new quote, I can say, is this a word I've seen before? And determine whether or not to score it. That's about as far as I got. The code I was looking at or trying to reuse, and we'll shrink it back down a little bit, was from there. Once I have my word counts, I'll have a new piece of text come in, and I'll say, given on a word-by-word basis for like the quote that I put in there. So I put in, I work very hard for a living. I was kind of gaming it towards I've looked at some of the men's quotes and was given an example. So split it up and then go through on a word-by-word basis and say, okay, what's the probability that this word came from the male dictionary or the female dictionary. And that just compares it to the total number of words that we have in our vocabulary and then the occurrences in that dictionary. And then so for the overall sentence, you can look at, okay, I have a higher percentage of male words versus female words. And then that's your final score. And then you run both of those through the classifier and then choose the maximum output and say, okay, based on all the probabilities that I've computed for the words, I've classified. So each word becomes an observable piece of data. Does that make sense? It's like each of those, so every word in the sentence is a way that we're updating the classifier. And okay, we have a new piece of observed information, and then the final is, okay, now we have the recommendation.
And every word has a probability distribution as well.
Right.
Because it occurs X number of times out of a total number of words.
Right. And that's the, that would fall under the, I think the normalizing constant. No, the probability of the class. No. That would be one of the probabilities that we use in the classifier is the probability of the word overall. So I apologize. I didn't get any farther than that. We can kind of work through if you guys want to and take a shot at it. I can give the helper function and the data and kind of work through the example, or if we have questions or anything like that, we can go from there.
I looked at the same example with the dino.
Yeah.
But I didn't get, I was having to set up my Python environment and get some problems. So I got to look at it, I got to run it, but I didn't get a chance to build it.
Yeah, theirs was a pretty clean example. They went at it a little differently, and a lot of their code and their overhead was on trying to get good training data. Right, so they wrote a lot on, we have a bunch of documents that we've classified as Dino versus crypto, and how do we parse all of those documents and build a training set off of that. This one was a lot simpler because I was able to just write the cleaning code and the computing the probabilities. But I think that's a good example, and that's why I kind of wanted to run through this one, and I'll probably complete it just to see, because what I would have liked to have shown is, based on the quotes that we have, let's try and score a couple. And then very easily we could go out and find additional quotes and add them in. So there was a couple of Socrata lists that had like 5 or 6 quotes from Mark Twain and 5 or 6 quotes from Winston Churchill. So we could quickly add those and show how fast the classifier could take in new information and improve the recommendation by having better data to train off of. The other thing I would have liked to have done was do a quick look in the room and say, okay, based on, we'll determine the probability of the class, which is to say, if my hypothesis is, male or female, so then we could compute from the room that we're in, what's the probability that you're a male, what's the probability that you're a female, just by counting up everybody in the room and determining that. And then that would go into, if we were scoring quotes from the room, we would add that in as a new feature. Right, so we'd say, we know the quote came from this room, so we're going to update and say, now based on that information, we know the distribution of the room is skewed one towards the other.
And that would be a change in prior.
Right, a more informed, rather than saying it's equally likely, it's 50% likely that it's male or female, just because that's where we're going to start with a uniform hypothesis. Instead, we would inform our prior by doing research and saying, okay, I know that the room that I'm trying to score is skewed one way or the other based on that.